All right, guys, so far with probability, we have done the basics. We've talked about the basic probability rules. We've talked about a complement, sample spaces, classical, aka theoretical probability, empirical probability, and we've used a couple addition rules. Today we're going to keep moving forward with our probability, and today we're going to look at some multiplication rules and something called conditional probability. So, here we go. Multiplication rules are used to find probabilities of two or more events that occur in a sequence. So up until this point, we've been looking at just selecting one student, just selecting one roll of a die. We've been doing just one thing, playing a game one time. What's the probability we win? Rolling two dice one time. That is what we had for our addition rules. Now that we're moving on, our multiplication rules, now we're going to be able to do two or more things in a sequence. So now instead of just selecting one person, now we can select more than one. Or instead of rolling a die once, we can roll it multiple times. So we're looking at a sequence of events. In order to decide which rule to use, our addition rules, we looked at mutually exclusive events. For our multiplication rules, we have to be concerned with independent and dependent events. So we're going to start with independent events. If two events are independent, the fact that event A, and I know we're just using generic A's and B's, we've worked with lots of different events, the fact that event A actually happens has zero effect on event B's probability of happening. So the fact that the first thing happens has no effect on the second thing happening. Doesn't change it at all. The two are totally separate. They are independent of one another. So if two events are independent, the multiplication rule, it's really straightforward. It's like when we had mutually exclusive events, all we had to do was add the two probabilities together. Now with independent events, we just have to multiply the two probabilities together. Please keep in mind, we have seen the word and. We have. In one of our activities, we wanted the probability of selecting a student that was a girl and said all students were friendly. That was just selecting one student. So we didn't do any multiplying. That was selecting one student. Now we're talking about two or more events. So not just selecting one student, but in this case we'd be selecting multiple students. So be very careful with that word and. And is going to mean we multiply, but only when that piece I've underlined happens. We have two or more events. We will also see the word and, like we've seen it previously, if we're selecting one thing, but we want it to have both characteristics. So be careful as we go. All right, so let's dig in and see what this would look like for us. Example 1, we're going to flip a coin and roll a die. Find the probability we get a tail on the coin and a 5 on the die. I'm just clicking to the second one so I can see how much space I have there to write. So what we want is we want the probability of a tail and a 5. If I flip the coin, does the outcome from the coin affect what I can roll on the die? No. Those things are separate. Those are independent events. So all I have to do to find the probability, and again, this is two or more events. Flipping the coin is event 1. Rolling the die, getting that 5, that's event 2. Those are two separate events. So the tail would be 1/2. Or actually, let me put the notation there just because we're getting used to it. So we're going to take the probability of flipping tails times the probability that we roll a 5. Everything we've done up to this point involving that word and, we always had that common denominator piece there. We were only selecting one thing, or we were just rolling the die, we were just flipping the coin. Only one event was happening up to this point. So the probability that we flip a tail is just a half. Probability we roll a 5 is a 6. Multiply, we just multiply across the top, multiply across the bottom. And there's our probability. In example number 2, it says a card is drawn from a deck and, keyword, super keyword, it's replaced, then a second card is drawn. I want to find the probability of getting each of those things. Now again, this is a sequence. We're going to draw one card, then we're going to draw a second. So up to this point, we've seen the word and before, but that was just when we were drawing one card. We could draw one card and we wanted to know if it was a heart and a queen. We've been finding probabilities like that. We've been using the word and, but that was just when we were drawing one card. No multiplication needed. Now we're drawing two cards. We have to decide, though, if the events are independent. So does drawing the first card in any way affect my probability for the second draw? Why doesn't it, though? What's the key that I know that makes this independent? It's replaced. If I don't replace it, then the second probability is affected. So we want the probability, queen, and ace. If I'm just drawing one card, drawing a queen and an ace can't happen if I'm just drawing one card. One card cannot be both of those things. This is a sequence of drawing two cards. There's a difference when you see the word and. It's how many events are involved as to what you do with the word and. So the probability I draw a queen, there's 4 in the deck. Probability I draw an ace, there's 4 aces in the deck. Now, if you want to simplify the fractions as you go, you are absolutely more than welcome to. I'm going to keep them for right now, 4 out of 52 and 4 out of 52. So if you refer back to your notes, you might see 1 out of 13 and be like, wait a minute, how did I get 1 out of 13? Why is it out of 13? There's 52 cards in the deck. This is also a nice opportunity for you to practice. Another reason to, if you haven't found your graphing calculator yet, enter those things in. Practice entering the fractions, practice making sure you get the correct multiplication, and then make sure you know how to use that handy decimal to fraction feature on your calculator. We want to, whenever we can, the simplified fractions, those are exact probabilities. We don't need to give some ugly rounded decimal answer when we have that technology piece that can help us out a little bit. Then the second one, really not a lot different. Queen and a queen. 4 queens in the deck. Keyword is that I'm replacing. So when I go to draw that second card, there are still 4 queens in the deck. There are still 52 total cards. So you have to make sure, I know we've talked the last couple of classes, that even one word can really change our probabilities. Even one word. All right, couple more with our independent piece, and then we'll move on and talk about our dependent. If we have a die, just a single die rolled 4 times, it says find the probability of getting 4 6s. If you want to go ahead and try these out yourself, if you want to take a shot at number 4 too before I go through them, please do so. Go ahead and try those couple out, example 3 and 4. If you're not sure on your calculator how to get it to do decimal to fraction, let me know and I'll help you out. If you kind of got rid of your graphing calculator, it's like, oh, chapter 3 is done, we don't need it. Nope, find it back. You're going to want it this unit too. You're going to want it this unit too, yes. And the next one, and the next one, and the next one, and the next one. You're going to want that graphing calculator from here on out. So if you didn't need one, use one for chapter 3. Make sure we're finding it for chapter 4. You're going to want it. Now, if you want to shortcut things in your calculator a little bit, like for rolling 4 6s, the probability you roll a 6, it doesn't change on each roll. So you're ending up multiplying a 6 together 4 times. So if you want to use that exponent, you can. 1/6 to the 4th power, rock on. It just makes it quicker, entering it into your calculator. Now the probability you get an odd number, again, maybe you went ahead and shortcut that, you put a half. That's fine. I'm going to put for mine.
Are you counting queens, kings, and jacks, and that stuff?
On a die?
Oh, sorry, on a die.
On a die. Yep, you're good. So there's 3 odd numbers out of the die out of 6 total. If you went ahead and just simplified that down to a half, that's okay. Again, I'm showing it as 3 out of 6, so we see that probability. And again, if you want to, you can use that exponent if you'd like. Now, I know some are like, wait, Miss Guy, why did you put dots for the multiplication sign for 4 6s, and then you did parentheses for the 4 odd numbers? I'm just showing you that either way is fine. However you want to show that multiplication piece. I know I didn't do the parentheses up towards the top, but you can do parentheses also for multiplication. If you really want to use that little X symbol, you can. I think I've totally stopped using that because it looks like the variable X. So now number 4 looks a little bit different. So if you're kind of sitting and waiting on number 4, we have the probability that a specific medical test will show positive is 0.32. If 4 people are tested, find the probability that all 4 will show positive. So at the probability of 4 positive, or if you put a 4 plus, that's fine too. And I know all we've talked about so far are independent events. We just have the one multiplication rule. So you're like, well, Miss Golly, these have to be independent because that's the section we're in. We still want to be thinking about, though, patient number 1, their test, the outcome on their test, is it going to change or affect the outcome for patient 2? No. They're not going to affect patient 2, 3, or 4. None of their results affect the other person's. So if I want 4 positives in a row, you're going to have that 32, that 0.32 or 32%, you're going to have that 4 times. So instead of writing that out 4 times, let's use that awesome exponent feature. And I don't know, my favorite number is 4, so I was really on a roll with that, I guess, when I did these examples. And it's okay, guys, that does come out. We got there, 0.32 to the 4th power. It doesn't work out pretty. And if you do your math fraction deal on your calculator, it's not going to change it. So here's one of those instances when we started day 1 in probability when I said, hey, fractions are going to be best because they're exact. But here's an instance where, you know what, we're not going to do all the work to get that fraction. I'm not going to change that to 32 hundredths and multiply that 4 times and try to change it. So we do use our rounding rule in this case. and we go to 3 decimal places. So I know for some of you are thinking, so Miss Golly, do I need that last 0 on there? Yes, because we are rounding. Our rounding rule says 3 decimal places. So we make sure our answer has 3 decimal places, regardless if the last one's a 0. So that's what we would round to. So I wanted to make sure we saw one. I know most of the problems you've come across so far have been very easy. The easy choice actually is the fraction. It takes more work to get the decimal or percent for what we've been working with. So I want to make sure we saw one and know those decimals are okay. You don't have to try to change that to 32 hundredths and raise that to the 4th power, then try to get it into a fraction. Don't worry about it. Especially if you start with decimals, stick with them, that's fine. All right, so that's just a little sampling of our independent events and how we would handle those with our probabilities and our multiplication. The other type then that we have to think about are our dependent events. Now let me shorten up this definition a bit for you here. 2 events are said to be dependent when the, kind of pick your word here, I would say occurrence, I think makes more sense. When the occurrence of the first event affects the occurrence of the second event. And let's just go such that the probability of the second event is changed. So 2 events are dependent when the occurrence of the first event affects the occurrence of the second event, such that the probability of that second event is changed. So the first thing happening affects the second thing happening, or the chance of the second thing happening, I should say. So independent, totally separate. The first thing can happen, it's not going to change the second one happening. Dependent, however, once that first thing happens, the chance that the second one happens has been changed. Doesn't mean it can't happen anymore, it just means it's changed. And we're going to see, we're going to do some examples just like we did with the independent events. So we will. Now the rule for this, and we will talk about the symbols for it. We are still multiplying. We do still have the keyword and. But again, this is still a sequence. 2 or more events. 2 or more events have to happen for the word and to mean we multiply. And I'm really, really trying to emphasize that because I know that each year come test time in this unit, I always still get a handful of students in every class that as soon as they see the word and, they think they have to multiply, even if just one event is happening. And then you end up with some crazy answers. The part that I want to stress on this is the notation for the second piece. And I already have this on your sheet. We have the probability, it has B and then a vertical bar A. What that symbolizes is that's the probability that event B happens after event A already happens. It's not a weird way. It does not mean B divided by A. It means the probability that B happens after A already has. So it's not B divided by A. And we're going to see through our examples that notation, it's not a big deal to worry about. It's not a big deal to worry about. So let's try a few of these. Let's see what dependent events are all about. All right, so we're back to drawing our card. And I know some of you are thinking, Miss Kelly, this example, this is just like example 2. Cards drawn from the deck. We just found a queen and then an ace and a queen and another queen. Miss Kelly, did you accidentally copy and paste the wrong thing? Nope. What's different? Whoops. If it will write, there we go. It's not replaced. So what that means, if we want the probability of a queen, There's my keyword and an ace. The probability that I can draw that queen on that first card, still 4 out of 52. I have a sequence of 2 events. I'm going to draw one card and then another. So that sequence, 2 or more events combined with that keyword and tells me multiplication is going to be the right choice. Now I don't replace the card. So how does that affect my probability of getting an ace? It's out of 51. I still have 4 aces. That's not going to change. But my total number of cards is down to 51. That's a different probability than 4 out of 52 that we saw with the independent events. So that little 3-letter word not made something that looks just like our example 2, totally different situation. So if we do a little bit of computation there, again, make sure, guys, we're practicing with our calculators. And then I know some of you are working ahead of me. Some of you probably have almost all these examples done already. Now, a queen and a queen. If it's going to be the same thing twice, in order for this to happen, a queen has to be drawn on the first card. Still 4 out of 52. Now, you have to make sure you slow yourself down for that second one. I don't put the card back. The card I don't put back is a queen. So when I go to draw that second card out, how many queens are left for me to actually get? There's only 3 left. How many total cards am I selecting from? The 51. So just be super careful when it's going to be the same thing twice and replacement isn't happening. That numerator is going to change along with the denominator. So just be careful on that piece. So we end up with, what do we got? 1 out of 221. So go ahead, if you haven't already, I know some of you, like I said, you probably had all these finished after I did the first one. Go ahead and read through example 6. Hopefully it doesn't make you too hungry here. We're not quite to lunch, but read through the cookie example. See if you can find those probabilities. Now, if you're struggling with finding that second one, raise your hand, let me know. We can talk about that. Put the answers up in just a couple minutes for you. Now, by eating the cookie, that means it's not replaced. Just in case you're trying to nail down that, how do I know? It might not always specifically say not replaced. It might be something that's implied, like the cookie being eaten, that things aren't being replaced. So just be careful. It might not always be the exact phrase replaced or not replaced. There might be something else in the wording that implies that. Again, today the thing I really want to stress, that keyword and can mean multiplication only if we have 2 or more events. If I'm just selecting one thing, I'm not using multiplication. I could just choose to select one student from this class and I might want to select a female that is a junior. I'm not going to multiply those probabilities together because I just want one student. Now, if I said I want to select two students, one junior and one female, now we would have that multiplication piece. So again, it has to be a sequence. We have to have two or more events. If you flip to the back side of your sheet, the last idea for our multiplication piece today is conditional probability. So sometimes we have the situation where we know event A is going to happen for sure. So we see that notation again. We have the probability of event B occurring is affected by event A occurring. So this is on the back side of your sheet. The little formula is already there for you, as is the definition. I'm just doing this for space. So this is the situation where, for example, we have two dice being rolled. It is known that the sum of the two numbers that occurred was even. So it is known, maybe we say that it's given. We know that that thing, yes, it happened. Event A is happening. Now that we know that that has happened, what's the probability that we get that second thing? So we have two dice rolled. If it is known that the sum of the numbers that occurred is even, find the probability that one number was a 2. So we want to find the thing that is given is event A. The thing that we want to know how the probability it can now happen is event B. So event B is the event we're still looking for. What's the probability now that this thing happens? Event A is the thing we're given. Event A is the thing we know this happened. Event B is what we're still looking for. So when we go to do our notation, we want the probability that we have 1, 2 given, or we know we have an even sum. So that vertical bar means given, or we know that second thing has happened. So the probability, we have 1, 2. If we know, or it's given, the sum is even. So our little formula, we want the probability that both things happen, and we're going to divide by the probability of the thing that we know for sure. We need to take that piece out because we know, hey, this happened. This piece happened. So what we need to do, take a look at our sample space, and we want the probability even sum and one of the numbers is a 2. So I'm going to, I'm sorry, my people at home open to page 187. Or if you're watching this video in the after class, 187. I'm going to put it up here for us so we can see. So y'all don't have to open your books. I know a lot of you yesterday got super familiar with this sample space. All right, so we want an even sum. We want an even sum, and we want one of the numbers to be a 2. So even sum, and one of the numbers is a 2. So let's take a peek. Even sum, one of the numbers is a 2. All right, so let's look through our 2 row and our 2 column. Let's start with our 2 row. 2 plus 1? Nope. 2 plus 2?
Yeah.
And one of the numbers is a 2. Nope. Yes. No. Yes. Let's do the column. Already counted. Don't count the double 2 again. Yes. And yes. So how many do we have? 5. We have 5 blue circles, right? On the board. So we have 5. Let me switch back here to my screen. So we have 5 out of 36. Here's a perfect example of the word and not meaning multiplication. I didn't multiply those things together. I want one roll of the dice, an even sum, and one number's a 2. Perfect example. We don't multiply to get that probability, even though the word and is there. This is one roll of the dice. It's not a sequence of 2 or more events. And then the denominator, we just want the probability of the thing that we know happens. So an even sum. Of those 36 outcomes, how many sums are even? Half of them, right? Now, I want to show you a little trick. Like, Miss Golly, why don't you just put a half there? It's going to be easier, right? Nope. Keep your denominators common because I'm going to show you a cool little trick. Well, it's something you should already know. What happens when we divide fractions? You multiply by the reciprocal, right? What's going to happen with the 36s? See you later. They're going to cancel out. So without me trying to type a bunch of fraction garbage into my calculator, I've got my final answer just because of my dividing fractions property. I want you to go ahead and try number 8. I will go through it. Then we just have one last little phrase to talk about today. Try out number 8, then we just have one last little phrase to talk about today. Oh, and let me put the cards up for my people. I know a couple people are opening books. Let me put the cards up for you. If you need it. I know I had a few people in each class yesterday relying on the cards. There we go. If you need the cards, I put them up on my screen for you. If you are joining me via Zoom or you're watching this video at a different time of the day, page 187 has a sample space for cards. That's what I have on my screen right now. I just can't share that with you. Here's my eraser. So sometimes it helps if we just label which event is which. Remember, event B is that second event. That's what we're trying to find the probability of. I put a box around the word given because that is indicating to me that this is a conditional probability. So what's the probability that we get a queen given the condition that the card is read? So the card being read, that's the condition that's met. If we were just asking to find the probability that we get a queen, that's different than just knowing that it's also a red card already. So probability that we get a queen, if we already know, or it's given to us, the condition has been met, that we also have a red card. So our numerator is the probability that the card is red and a queen, divided by the probability of the thing that we know, yes, this has happened. That word and in the numerator, remember, we're not multiplying here because we're just picking one card. If I were picking two cards, we'd multiply, but I'm just picking one. So the word and in this case, we just want to find how many cards have both of those characteristics. All right, so we have how many red queens? 2, I believe. 52 total cards. Probability it's red? Half of it. Now, because we keep the denominators the same, we know those 52s are going to simplify out. So I often get the question, Miss Golly, do I even have to write those 52s? Or in the example above, do I have to write the 36s? No. Once you get comfortable with this, if you know those are just going to simplify and you're going to be left with 2 out of 26, you can jump right there. That's fine. That's fine. I kind of hope we get to that point. Save yourself that step. That's okay. That's the idea. How many red queens are there? There are 2. How many red cards total? 26. So you're limiting your sample space to this outcome. How many red cards? 26. So that's my new total. If you need the formula, great. If you don't, that's okay too. The formula's there if you need it. Our final piece. And I've been talking about the complement. And here's where it comes in handy. There's going to be a phrase in some of our questions, at least. We've talked about at least before. What did at least mean, though? More than, right? That number or more. So at least would be that amount or more. So even though it says least, our brain still has to switch gears and go to that more piece for us. So, for example, these are just easiest to dive right in. There's really not a definition. There's not going to be a, here's the rule, here's the formula. We have 4 letters of the alphabet are selected at random. Find the probability of getting at least one letter J. So what we could do at least one J. What we could do is have to take the time to figure out the probability that we get one J plus the probability that we get 2 J's plus the probability that we get 3 J's plus the probability that we get 4 J's. Now, I know some are thinking, oh, that's easy, Miss Golly, just add some fractions together. We're selecting 4 letters, though. So I have to select 4 letters for this probability and do that multiplication. I have to do the multiplication for selecting 2 J's and 2 of something else. I have to do the multiplication to select 3 J's and 1 of something else. And I have to do the multiplication to select 4 J's. That sounds like a lot of work. Doable work. It's not too tough to multiply those things together, but it takes a lot of work. So instead of having to figure out those 4 separate probabilities involving selecting 4 letters, so multiplying 4 probabilities together for each one of those and then adding them all together, instead of worrying about 1 or more, what's the only case I haven't considered? How many J's? 0 of them. Probability, at least 1 J, the complement of that is the probability of 0 J's. That's just one I have to find. Because remember, the probability of the event plus its complement always equals 1. Always equals 1. So if I want to find the probability, I can do 1 minus the complement. It makes life a lot quicker on these types of questions. So the probability that I get 0 J's, 25 out of 26 letters are not J. For the second pick, 25 out of 26 letters are not J. Not J. And not J. Or you can do that to the 4th power if you would like. I'll probably do that. So these are not J's. Man, that number 4 again. All right, my calculator doesn't want to change it to a fraction. That's okay. I'm going to go 3 decimal places. Yep, 5, 5. There we go. So that thing we had to do to find 0 J's, that's what you would have to do to find the 1, the 2, the 3, and the 4. You would have to do that process 4 times and then add them all together. Or we can use our complement rule, and we can just subtract 1 minus the complement. Remember, these two things, the event and the complement, if I add them together, it equals 1. The event plus the complement, if I add them together, I get 1. So this is a case where I could find this. I could find the probability of 1J, then 2, then 3, then 4, and I can add them all together. It's going to take a lot of work. Or I can find the complement, which would be 0 J's, and I can subtract from 1. So when you see that phrase, at least, you might have to end up finding a whole bunch of probabilities and adding them all together. Or you can use the complement and make life a lot quicker and easier. So play around a little bit with example 10. See what you think. See what you think. Try using that complement idea. Try it out. We are going to go through it. If you want to work with people around you, that's cool. Try it out. So instead of having to worry about 1 and 2 and 3 and 4, let's just worry about the 0 and subtract from 1. The event plus its complement equals 1. See what you think. Now, Sally, can I, if I want to, can I find 1 senior, and then 2, and then 3 and 4, and add them all together? You can, sure. You'll get the right answer. It's going to take you a whole lot longer than doing the complement way. but you can. So if you wanted to do it the long way, you would have to select one senior and then 3 of something else. 2 seniors, 2 of something else. 3 seniors, 1 something else, and then 4 seniors. You'd have to find those 4 individual probabilities and add them all together. In each of those individual probabilities, you'd be multiplying 4 different things together to get each one of those. It's going to take a lot of time. So instead of worrying about at least 1 senior, which means 1, 2, 3, or 4 in this case, I can think about the complement, which is the thing that's not included, which is the case of 0 seniors. If I add the complement to the event, if I add those probabilities, I get 1. That's why I can do the 1 minus. So the probability of at least 1 senior, the complement, I want to make sure I write that out so you can see it, so you can see my work on there. So the complement of that, so we're talking about 0 seniors. We don't want any seniors. So we have a total of, what do we have? 6, 4, 13 people, right? Okay, so we're going to start with 13 people. And how many of them are not seniors? 7. Now, here's where you have to be careful, and some are like, oh, Miss Golly, I kept it out of 13 the whole time. If I'm choosing a committee, can I pick the same person for all 4 spots? No, I can't. I can't pick the same person for all 4 spots. So, the next number I would have, the next fraction would be 6 out of 12. Now I'd have 5 out of 11, and I would have 4 out of 10. Again, that's where some of those pieces, some things are implied there. It's not saying that, oh, I replaced each person or I didn't replace them. It's implied here that I can't replace. I can't replace those students. If I want a committee of 4, I can't pick the same person to fill all 4 spots. I need a committee of 4 people. So sometimes that not replacement, it's implied by what you're trying to select. So you have to be careful with those. And this is simplified 7 out of 143. So we're going to do 1 minus 7 out of 143. We have 136 out of 143. So again, this idea of at least is just really bringing in that complement idea. I know earlier when I talked about the complement, using it was like, that just seems like something extra to remember. But now it's a huge time saver. What if we were selecting a committee of 10 people and you wanted at least 1 senior? Now you have to figure out 1, 2, 3, 4, 5, all the way up to 10. That's a ton of probabilities to figure out. I mean, what if we had 60 seniors and 40 juniors and 30 sophomores, and we wanted to select a committee of 10 people. We want at least 1 senior. It's a lot of multiplying together. So make sure you're trying out those rules, okay? For your assignment piece, I put on there, guess it's not on my presentation, I apologize. For your assignment piece on your handout, I suggested 1 to 51 odd. Then I also said, well, I would suggest doing all if you have time. I would go through first, though, and do the odds. Now, remember today we looked at independent events, dependent events. We also had conditional probability, and we had that at least idea. 4 different things in this section, 4. So if I just do maybe the first quarter or half of the assignment and think, oh, this is easy, I might not get to that stuff that maybe takes a little more thought, like that conditional probability and using that complement for the at least. If you don't get to those end questions, It's going to come review time, and some of us are going to be in the same place we were for chapter 3. What do you mean, at least? How do I do that? Or wait, how do I handle it if I'm given that the card is red? Make sure you get to those end problems. Otherwise, this test will be a very confusing place for you. So make sure you try them all, and then go back and do the evens for some more practice.
Yeah.
Yeah.
What is the